Hello and welcome. This is going to be our lecture video for the Unit 7 Energy Test Review. Let's go ahead and get started with number 1. What is the kinetic energy of a 23 kilogram printer moving at a velocity of 7 meters per second? So when we see kinetic energy, we'll go find our kinetic energy formula. We can plug just straight into this formula as long as our mass is given in kilograms, which it is, and our velocity is given in meters per second, which it is. So other than that, this is just making sure we evaluate this formula correctly and give the correct units. So kinetic energy equals 1/2. I'll use a 0.5 because that's easier to plug into my calculator, times mass, which is 23, times the velocity squared, 7 squared. I can plug that all in one line in my calculator, 0.5 times 23 times 7 squared is 563.5. Now, run that backwards, 563.5, and now we have to give the right unit. The unit for energy is joules. All right, let's try the next one. So a 5-gram nickel. So now the formula won't work because this isn't in kilograms. I need to do a quick conversion of 5 grams to kilograms. So I should know that there's 1,000 grams in 1 kilogram. To evaluate this, I do 5 divided by 1,000, and I get 0.005 kilograms. Velocity is given in meters per second, so I can plug this into my formula now. 0.5 times 0.005. So those are very small numbers, but when I do the 343 squared, that's a very big number. Let's see what we get. 0.5 times that times 343 squared gives us 294.1 joules. We can just round a little bit. All right. Now on to gravitational potential energy. So this is a different formula for energy, still measured in joules. But this is the MGH formula. If it's done on Earth, G is going to be 9.8. Height must be in meters, mass must be in kilograms again. So again, I've got kilograms, I've got meters. So I'm ready to plug this one in. 40 times 9.8 times 40. And I get 15,680 joules for this one here. All right, in number 4, we don't have meters. We need to convert the 2 kilometers to meters. So know that 2 kilometers is 2,000 meters, 1,000 meters per kilometer. And you can plug that one in. Number 5, now we've been given the information in a different order. We'll still use our kinetic energy formula, 1/2 mv squared, but we fill in different parts of it. The motorcycle weighs 185 kilograms, so that goes in for the mass. 0.5 times 185. But we don't know the velocity, so equals v squared, but we do know the kinetic energy is 34,000. All right, we can multiply these and get 34,000 equals 185 times 0.5, 92.5 v squared. Divide both sides by 92.5. And we got 34,000 divided by that number gives us 367.6 equals v squared. And then how do we get rid of the squared? We use a square root. So just take the square root of that number in your calculator. And we get 19.17 equals the velocity. But here's where units are very important. You need to know that this velocity is in meters per second because that's the unit that our kinetic energy formula requires velocity to be in. But we wanted kilometers per hour. So now we've got to do a bit of a unit conversion here. So start with 19.17 meters over seconds for the per second. We will multiply by the fact that there's 1,000 meters in 1 kilometer, and the fact that there's 3,600 seconds in 1 hour. Sorry, I'm running out of room here, but I multiply across the top, multiply across the bottom, and divide. So times 3,600 divided by 1,000, and I get 69.02. We'll just round that to 69 kilometers per hour. So 69 km per hour. So expect quite a few unit conversions on here. And you have to really know your metric system to be able to deal with kilograms, milligrams, anything with a kilo or a milli. You should be able to do that perfectly at this point. All right. We've got another one where we just solve for the missing variable. This one we're solving for mass, so you don't have to worry about any sort of square root. Everything's in the correct units. And you'll just answer in kilograms. Number 7, we're solving backwards for gravitational potential energy. So let's plug these numbers into gravitational potential energy. So 2778.3 equals the mass, we don't know the mass, times gravity, 9.8, times the height, 10.4. Multiply these together and divide it from the 2778. So 2778.3 divided by, I'm just going to do it one at a time, 9.8 divided by 10.4 gives us a mass of 27.26 kilograms. So that is a very heavy bag of pennies. It's like over 50 pounds. All right, and another one where we're just solving. Here we have no kilograms is good, and for the height we'll just answer in meters. All right, next page. All right, now we've got some questions about power. Let's go on to number 9. 2 physics students, Will and Ben, are in the weightlifting room. Will lifts the 100-pound barbell over his head 10 times in 1 minute. Ben lifts the 100-pound barbell over his head 10 times in 10 seconds. Which student does the most work? So this is a bit of a trick question because they both lifted the same amount the same number of times. They just did it in different time intervals. Well, time isn't part of the calculation for work. So this is a trick question. They did the same work. Work is just force times distance. Lifting it requires the same force, whether you lift it very quickly or very slowly. And we can prove that because the barbell gains the same amount of gravitational potential energy either way. And since energy must be conserved, the same amount of work must have been done. Which student delivers the most power? Now, power doesn't incorporate time. So the student that lifted it in 10 seconds, Ben, because he was able to deliver that same amount of work in a faster time, must have more power. Remember, power is measured in watts or joules per second. So it must have been Ben there. All right, number 10. A squirrel of 1 kilogram does push-ups by applying force to elevate its center of mass by 5 centimeters in order to do a mere 0.5 joules of work. We could prove that it's 0.5 by just multiplying force times distance here. Force is in newtons. We'd have to multiply the weight by gravity. If the tired squirrel does all this work in 2 seconds, then determine the power. So power is just work over time. So if they did 0.5 joules divided by 2 seconds, we will get 0.5 divided by 2 is 0.25 joules per second. Well, the word for joules per second is a watt. So 0.25 watts of power. Think of a watt as how quickly we can transfer energy. Here, the energy we're transferring is the chemical potential energy in the muscles of the squirrel into gravitational potential energy in the form of it being higher up. And it did it in 2 seconds, so 0.25 watts. On to number 11. This is a common question. How many joules is a kilowatt hour? So let's start with that unit, a kilowatt hour. So 1 kilowatt hour is not 1 kilowatt per hour, it's actually times hour. So both of those units go to the top of our unit conversion bar. All right, and let's turn kilowatts into normal watts by multiplying by 1,000. So 1 kilowatt is 1,000 watts. That will cancel out kilowatts. And let's get hours into seconds. It'll be clear why in just a second. 1 hour is 3,600 seconds. So now hours are gone. And we get, let's see, that'd be 3600, and then add 3 more 0000. 3,600,000 watts times seconds. Well, a watt is just a joule per second. So joules per second times seconds, the seconds actually cancel out here. And a watt second is just a joule. So the real answer is 3,600,000 joules in 1 kilowatt hour. All right, number 12. So another one about power. So elevator is moving 20 passengers every minute from the first floor of the department store to the second. Second floor is located 5.20 meters above the first floor. The average passenger's mass is 54.9 kilograms. Determine the power requirement. So the easiest way to figure this one out is figure out how many joules of gravitational potential energy we've gained, and that has to be equal to the amount of joules we've transferred. So mgh, the mass is going to be 20 passengers times their individual mass of 54.9, times our gravitational potential energy of 9.8, times the height, they were raised 5.2 meters in the air. Multiply all four of these numbers. And we see our passengers gained 55,954 joules of energy. All right, now that's the number of joules transferred. How long did it take it to happen? Every minute, so that's 60 seconds. We'll divide by 60 to get that the wattage, or kind of like the watt rating of this escalator is 932.6 watts. So it's probably evaluated to do much more just in case a bunch of people get on it. But you only have to actually draw the amount of electricity from the grid as you need to accomplish the amount of work. So it would have drawn close to 1,000 watts of energy from the grid. All right. There's a kind of fun conversion here to horsepower. I forget what it is. But we can figure out the horsepower of this escalator. I just looked it up. The real number is somewhere in the 700s. So this escalator is running on about 1.5 horsepower to move everybody. It's probably rated at something more like a 5 to 10 horsepower just for when it's crowded. All right. What is the ideal mechanical advantage of the following inclined plane? So there's two ways to figure out mechanical advantage. You can do output force divided by input force, or you can do input distance divided by output distance. These should be just correlated, and that's why we're able to equate these. Notice in one of them you got output on the top, the other one you got output on the bottom. So this one we are given distances, so we'll use this formula with distances. Our input distance here is 24. Our output distance is 5. Those are both in meters, but that cancels to give us a mechanical advantage of 4.8. That's the ideal. We know that we will never achieve that because of friction. All right, with number 14, we need to figure out what the actual mechanical advantage of this inclined plane is. So we're only given 2 numbers. That's all we need. We're going to use the effort definition. So the output effort is going to be this 35 newtons because that's the effort required to draw something straight up. So all we care about, even though this brick is going to move to the right, it's also going straight up. So its output effort is 35 newtons. The input effort is right here. So that's going to be output force and input force. And we just divide the two. So 35 over 15 means that this inclined plane gave us a mechanical advantage of 2.33. So it should definitely be more than one. Inclined planes reduce the amount of force needed. But just think about it this way. To pull it straight up requires 35 newtons. By using the plane, we reduced that to 15 newtons. So we're clearly gaining a mechanical advantage. And then it's just the proportion between those that is our mechanical advantage. All right, now number 15 just gives us a bunch of numbers to figure out this thing called the efficiency. Real quick, efficiency, let's try to underline that, is your actual mechanical advantage divided by your ideal mechanical advantage times 100%. So we'll figure out based off the math what the ideal mechanical advantage is, then we'll figure out the actual mechanical advantage and figure out what the percentage is there. The best we could ever do is 100% efficiency. All right, so ideal mechanical advantage, we'll just do the distance formula for that. So ideal mechanical advantage is going to be input distance divided by output distance. 12 divided by 2 equals 6. But now to figure out the actual mechanical advantage, we'll look at the actual forces involved. We went from 783 newtons to lift it straight up down to 150 newtons to pull it sideways. So the 783 divided by 150 gives us an actual mechanical advantage of 5.22. So pretty good, but we were robbed by friction a little bit. Let's figure out our efficiency here. 5.22 divided by 6 times 100% gives us 87% efficient. That's very good for an inclined plane. Levers are often much more efficient than inclined planes. So let's take a look. Again, we'll figure out ideal mechanical advantage and then actual mechanical advantage. So ideal mechanical advantage, we'll use the distances here. With the length of the lever arm and the effort arm. So we're pushing closer in. So we should actually get a mechanical disadvantage here. And that's actually what we see. It takes 57 instead of 45 to lift this thing. So we need to set it up so we get the disadvantage. 5.8 over 6.3 gives us an ideal mechanical advantage of 5.8 over 6.3, 0.92. So why would we want to take a disadvantage? Well, although we've got a disadvantage, this block is going to be lifted much quicker. So maybe we want a machine that lifts this block very quickly in exchange for more force. All right, and then the actual mechanical advantage is the 45 newtons of force to lift this straight up versus the 57.7 that we actually applied to the lever. And we get 0.779. And now we'll just compute that as a percentage. 0.779 over 0.92 times 100% is 84.8% efficient. All right. All right, with number 17, list the 3 types of levers, draw a picture and write an example of each. I am not going to list them here. I'm going to let you do your own research for that one because this is a very easy one to look up, and they will give you lots of great examples for these. But expect a very similar question on the test. So do your own research on number 17. 18, question about calories. How many calories, little c calories, always pay attention to the capitalization there, are needed to heat 40 grams of water, 10 degrees Celsius? So all we have to do is just the 40 times the 10 here. And that's because the specific heat of water is 1 calorie per degree per gram. So it's just multiplying the two numbers. It's just as simple as that. This is 400 calories. 1 calorie will raise 1 gram, 1 degree. So 400 will raise 40 grams, 10 degrees. All right, a food contains 300 big C calories. How many joules of energy does it contain? So here, watching out for the capitalization, we need to do a little conversion here. 300 big C calories multiplied by the fact that it's 1,000 little c calories is 1 big C calorie. And there's another conversion we need to know is that 1 calorie is equal to 184 joules. All right, I just double checked it. It is 4.184 joules. So now let's multiply 300 times 1,000 times 4.184. Means that in your 300 calorie snack, we have 1,255,200 joules of energy. Food contains a lot of energy, so expect big numbers when we're dealing with big C calories. All right. If I burn some peanuts that have 50 calories, which would be 50,000 little c calories, and heat a beaker with 30 milliliters of water and capture 100% of the energy, how much will the water heat up by? So that's going to be 30 times x. So we'll just do that 50,000 divided by the 30 to get that it should, in theory, increase by 1,666 degrees Celsius. Obviously, that's not going to happen because as soon as it accepts that energy, it'll start dissipating again, and you'll never actually be able to increase something by that much. But that's the theoretical amount. All right, 1 liter of water. So don't be tripped here. 1 liter is 1,000 grams. Well, it's 1,000 milliliters, but it's 1 milliliter to 1 gram, so it's 1,000 grams. It's heated 40 degrees, so just times 40 degrees, and that will give us our calories of 40,000 little c calories. Now to get big C calories, move the decimal point 3 times, and we get 40 big C calories of energy in that water. All right, that's that for this lecture video. Have a good rest of your day.